So welcome to the last day. Appreciate all your attendance, and it'll be a little bit more flexible today than some of the other days because we're going to get into discussions this afternoon about kind of culminating everything as a workshop in a whole. So before that, we have our last readouts. We skipped the neural network readout, so I'm actually going to share my screen. I'm going to attempt to do this and play a video. So let me know if you can see my screen.
Yes.
All right, I'm going to try this. Let me know if it's bad.
Hello and welcome. This is Arup Ganguly. I'm the session chair for the Crosscutting Neural Network session. We have 7 session co-leads and 7 session.
Oh, we lost audio.
The 7 themes are the following. The Earth System challenges motivating neural networks was the starting theme, and the ending theme was next generation neural network, which can help Earth System models and processes. And then in between, we have neural network enhanced physics, data challenges in neural networks, physics guided neural networks, physics informed uncertainty quantification, and then explainability and interpretability. In terms of grand challenges, we talked about a couple of broad points. First of all, how can neural networks help scientific discovery? And secondly, how can they yield stakeholder insights? And hopefully one relates to the other. One of the themes that came up again and again was extreme values and regional change. And within that context, also things like uncertainty quantification, extraction of causal insights. And in addition to extreme value and regional change, things like tipping points, emergence, missing processes, and non-stationarity in climate. So when there are changes in the planetary radiative budget, what that might mean for certain equations, etc. So this is the kind of constrained non-stationarity, if we can call it that, that we see in the context of climate and our systems. And then one thing that came up a few times was, could we provide theoretical guarantees or some bounds on generalization performance? It's not just out of sample, which is of course one of the things, but it's also generalizing to future conditions, which at least at that point in space may not be the same as current conditions. And then uncertainty quantification, prediction accuracy, dealing with big data, small data challenge, especially in the context of heterogeneity of certain processes such as land surface. Interpretability and how interpretability and explainability can be robust to these different kind of data challenges, and then building hybrid physics and neural network, which go into deep learning approaches. In terms of state of the science, neural networks have been used for Earth system model parameterizations, either to replace or to improve, and recent studies in atmosphere, hydrology, and ocean suggest that there is some value to using deep learning based parameterizations in each of these contexts, especially to model subgrid scales. And then when we look at neural networks to extract insights, a couple of years back, there was this perspective article in Nature, which talked about deep learning and process-based understanding. In the context of Earth system science, they talked about machine learning tasks, such as object classification, image super resolution, video prediction, language translation, which then helps in Earth system model tasks after adaptation or after further development, such as pattern recognition, statistical downscaling, blending, short-term forecasting, such as quantitative precipitation forecasting, and dynamic time series modeling, such as El Nino. And these kind of work have appeared in the recent literature in interdisciplinary journals such as Nature, as well as in artificial intelligence and data science / machine learning conferences such as KDD, ACM KDD, and ICHKAI, the international joint conference on AI, as well as knowledge discovery and data mining. And then For neural networks to be useful in Earth system processes, they have to be interpretable and explainable, and a lot of work has happened there recently in weather prediction, climate signal detection, remote sensing, such as land use classification, satellite sensing, etc. In terms of experimental data and modeling opportunities, there are opportunities for field experiments in data-poor regions, new sites, sensors, or sensors, whether these are DOE, whether they are NASA, and then computer-based experiments to estimate value of new data. The kind of opportunities, we have different kinds of data. We have observed data, model simulated data at different scales, weather prediction, regional Earth system models, global models, and we could generate synthetic data, both from resampling as well as from neural processing, such as adversarial networks and autoencoders, including we could simulate synthetic data at tails, and we need to then curate data, share data, standardize data, and ensure fair principles, findability, accessibility, interoperability, reusability. We need to understand uncertainties and look at modeling scales across a suite of modeling simulations, which can be thought of as test beds of varying complexity, and then understanding how neural information processing can deal with multiple scales, how causal inference engines can work, and how weather and regional climate simulations can work in tandem with global system processes. In terms of research priorities, extreme values and distributional tails came up again and again, as did regional change and tipping points. The kind of non-stationarity that we expect in climate and the kind of process heterogeneity led to these discussions around theoretical guarantees for generalization bounds, performance bounds, uncertainty quantification, especially in the context of hybrid physics and neural network or machine learning models, and comparisons of various types of these neural network, machine learning, Earth system process of these and hybrid combination. Evaluation and maybe part of automation or semi-automation of neural network training, architecture, hyperparameter, extraction of causality, making interpretability robust to different data challenges, potentially transfer learning from big data to small data scenarios, understanding value of new data from computer experiments, and then generating model simulation test beds, big data and small data repositories, which are AI ready, which are standardized, which follow FAIR standards, optimized for HPC, and to some extent, either automated or semi-automated. And then when we come to the goals in short, medium, and long term. So first of all, we need to create these model simulation test beds, these big data repositories. Then we need to create and evaluate and potentially semi-automate these neural network training, architecture, causality, interpretability, which are incredibly important in scientific discovery and credible, issuing stakeholder relevant insights in a credible manner. Once we have all of that, given that we are dealing with certain kinds of non-stationarity and heterogeneity, only once we have that, we can deal with the key challenges, such as extreme values, distributional tails, regional change, tipping points. And then we get to somewhat more focused challenges, such as could we transfer learn from big to small data scenarios, could we understand value of big data, and finally hopefully automate this process to the extent possible without taking out the human expert or domain expert, of course, but automating things like, for example, hyperparameter search to the extent it's feasible, and then ensuring theoretical guarantees to generalization bounds uncertainty, especially for hybrid physics neural network systems.
Okay, glad that timed out. I wasn't sure what would happen there. Stop sharing. Okay, next up is Siva. Are you ready? I don't actually, there you are. I do see you now. Would you like to give your report out next?
Hey, Nikki, the 4 breakout chairs are going to share their screen and do that.
Great, wonderful. I'll leave it to you guys.
Prasanna, you want to go first? We can see your terminal. Yep, but we don't have audio.
This is good?
Yes.
Okay, thank you. So this is a summary of 2 sessions. So I will be covering part of it, and the other session, breakout lead will be covering part of it. So let's get started. So from the grand challenges perspective, right? So, there is a lot of talk about how to build models and so on and so forth. But when we are talking about AI and machine learning, data is the key. And the data quality, especially if you're talking about building machine learning models and AI models, 80% of our effort goes into preparing the data. So how can we automate that process, prepare data preparation and analyzing the error, uncertainty, and characterization? I think that is a grand challenge. The second challenge that we talked about is bridging the scale and the resolution for both models and the data. And from the hybrid modeling perspective, the numerical stability. So yes, we can do something, with the combination of the machine learning model and the physical model. So as soon as we combine, we can do some forecasts, but then the numerical stability of the models, is a big challenge and a limitation. So, working towards solving the problems related to numerical stability is a challenge. From the mathematical perspective, this is a large, training models, and related even in the case of physics-informed neural networks. It's a minimization problem that is non-convex and it's very large scale. So we need new set of mathematics that are sort of customized to the Earth system predictability modeling that can solve this type of training problems. Error propagation is another aspect where we are going to combine multiple models and multiple physical models and multiple machine learning models, how to propagate error from one of these to the other and across different time scale, across various temporal and spatial scale. That's a very open question. On the software side, we need open source high performing software tools and how to scale them. So in terms of state of science, mostly, despite number of papers that were written and despite number of sort of demonstrations that were there, these are mostly prototypes, and except few proof of concepts at scale, it's not widely adopted. So in some sense, state of science is really promising, but we are just scratching the surface in terms of possibilities for hybrid modeling. There are a lot of opportunities. First and foremost, how to utilize all the data that we are collecting. The very fact that we have a great infrastructure in terms of ARM, in terms of the new data modalities such as 5G, ability to collect data at will and with the low latency, high bandwidth, and so on and so forth. We are going to collect a lot more data, but the question is how to utilize all this data in a systematic way. And speeding up simulation, in particular, if you're talking about hybrid modeling, speeding up simulations, it's one of the key goals why we want to do hybrid modeling, why we want to do emulator, why we want to do surrogate modeling. So there are a lot of opportunities for speeding up simulations. Again, coming back to the data, machine learning to develop methodologies to acquire data, and the discovery of physics, systematic error analysis, and so on and so forth. So those are all various types of opportunities that exist. In terms of short-term goals, really in a 1 to 2 years, showing significant like 10x speed up in real simulations, either in WRF or other type of Earth system simulations, showing like, okay, with this existing technology, can we do 10x speed up? This will bring together multidisciplinary communities, and as you all know, machine learning progress because of benchmark data sets. So we are thinking of like, what is the next sort of ImageNet data set from Earth system predictability perspective that can allow us to do hybrid modeling. The 5-year goal is 10x to 100x speed up in simulations, and then all the related technologies that we need to develop to achieve that target. In 10-year goal, the 10-year goal is really 1000x speed up in the simulations. So what we are looking for is 1 million model ensembles. What we are doing now is like 30 model ensembles or 50 model ensembles. But if we have to do at a zeta scale or a iota scale, 1 million model ensembles, then the kind of rare event simulations and rare event are assessing the risk with the rare events that we are expecting. Our ability to model them will increase many fold. So that's a sort of a 10-year goal. And related technologies such as mathematical framework for uncertainty quantification, and more importantly, automated model development that was already mentioned in the previous talk, and physics discovery. So it's not just model discovery, but can we use AI to discover new physics? That's an ambitious 10-year goal, and also sort of related technologies.
So Prasanna, can you leave the slide just there? And because Nathan and you are going with the same slide. Nathan, you want to go next?
Yeah, so there's a lot of overlap here. So many of these bullet points are just consolidated, but I'll pick out a few things that I think distinctly came up in our breakout session. So one of them is online training and data assimilation as potential opportunities for applications of hybrid modeling, as well as active learning. So not just training passively off of whatever simulation data has been generated, but choosing which simulation data to generate in order to better train hybrid models. And then just moving up into goals, we definitely had a lot of emphasis on uncertainty quantification. I mean, in the short term, just doing any uncertainty quantification would be good because we're still struggling to get hybrid models working in the first place. And we thought basic steps could be made in that direction. Going into the future, we're talking a lot about integration of hybrid models into DOE codes from a software perspective, and whether you could do this within high-level programming environments, not just Fortran, and what kind of software would be needed to do that, whether you can differentiate through it and get adjoints or derivative information to allow you to do gradient descent type ideas or other sorts of traditional things you do with adjoints. Getting the models stable is one thing that was emphasized over and over again, since we still have very little guarantee that they will be after training. And then longer term, online coupled training came up again, and how do you train and validate at climatological timescales and really make sure that it's going to work over 100 years. Having a fully worked out framework for doing UQ in this hybrid setting, and developing again the software frameworks so that it becomes more routine to be able to train, couple, validate, and accelerate hybrid models.
Thanks, Nathan. Peishi, you want to go next?
Okay, I will share my screen. Okay, can you see my slides?
Yes. Just slideshow mode.
Not share slideshow. Yeah. Okay, so this is the summary of another breakout in our hybrid modeling. So in grand challenges, we identified the following. First, there's still need to achieve the computation efficiency of running Earth system models like all the other sessions. Second, there's a need to deal with the multi-fidelity simulations and observation data sets. And third, we think the current performance or the performance of the current state-of-art machine learning or AI models may not be powerful enough that is able to capture the performance of the complicated Earth system models like the multi-physics and multi-scale models. And the fourth is we think we need to evaluate the trustworthiness of the future of the current developed hybrid modeling. And there's still also a need to address the technical problem of how to integrate the Python-based machine learning codes with the C++ and Fortran-based models. State of science. As we all know, we have a lot of various efforts that focus on integrating the partial differential equation into machine learning models like the physics-informed neural net and Fourier neural operator and so forth. but there are limited applications of machine learning in integrating the model simulations and the observation this data sets, and there are limited applications of machine learning models in couple physics models with the machine learning codes. And we've seen less work in few shot or even zero shot learning for the physics informed neural net. And opportunities. So given the increased availability of the data set, like from NASA reanalysis product or all the other remote sensing data, so these data sets give us the opportunity to integrate them into the Earth system like models like ES3M using the hybrid modeling. And due to the advance of the computing power, we have more capability to do large scale simulation at fine spatial and temporal scale. But that can be both a challenge, but also as it is an opportunity to get a validation data set. And we also see a lot of emerging tools that offer promise to accelerate the coupling of the machine learning code into the physics models, like using the JAX or Fortran Keras. And there are several distributed or decentralized repository of data sets that support machine learning or AI implementations. And AutoML is also a way to assist or facilitate or accelerate the development of the hybrid models. Research priorities. We think the most important thing of developing the hybrid models is allow it to address or account for the rare or extreme events. And differential climate modeling is also a priority so that we can train the hybrid models using propagation like we did for the traditional machine learning models. And the software and the framework issues is also a priority that we need to address to coupling hybrid modeling more efficiently. So in the future, in the short term, we think we still need to continue the effort in formulating the machine learning model so that the projections can be interpreted between training data in a better way. And again, software engineering issues is a technical problem always to integrating the Fortran-based physics model and machine learning models. And in the long term, we also need to formulate the machine learning models that I mentioned before that is able to account for the rare events, and using techniques such as the few shot or zero shot learning, enhancing the explainability of hybrid models is also a need, and developing techniques or models to address the differentiable climate models is also a need. And last is we need to develop some systematic approaches to enable the machine reasoning.
Thanks, Paishi. And GLE will be our last summary.
Yes, I'm going to share my screen. So I also realized many points are very similar between our different breakouts. So I'm going to only talk about that the points that maybe other breakout didn't mention or didn't touch. For the grand challenge, we found there are a lot of data challenges based on the domain science we're doing. For example, there are many small scale processes, but it's in a large space. And also it is affected by human impacts, such as the hydrology or biogeochemical processes. And those processes are expensive to simulate, and the models are very expensive to run to generate enough data. And also there are many processes that are not well understood. And also because of all those reasons, and there are a lack of data archives that are available immediately in many research areas for machine learning development. And in terms of the process model that we use for developing the machine learning model, those models, we do not always have a good understanding about which component is actually have a high confidence or ready to be emulated and which are not. So we should have a good understanding about that. In terms of training, since we were talking about, the whole session is about hybrid modeling. So there need to be not offline training about emulator, but we also need to make sure the machine learning emulator that we develop works as good when it's going to the online combined with the PDE. And there is such challenge. For example, the numerical challenge, when you bring back the machine learning emulator, very likely you will see a stability issue. And more straightforward, for example, when you trained offline, you use an input data set, but when you put it back in the Earth system model, the input data set changed. And how to incorporate those change by using observation data, by conducting more training online. And also there is this non-stationary in the data set, especially when we consider historical versus future. And also how do we verify them? The model we are developing. How can we tell it's good or not? And right now, most of the evaluation will just look at the number, right? Look at whether the machine learning model or the hybrid model captures that magnitude. Is it within a reasonable magnitude? But why? We need to understand more about the causal relation for those hybrid models. And we also talk about the error debugging and the uncertainty propagation. And as we all know, there are uncertainties in each of the components, no matter for the machine learning development or the process model, and how can we quantify those uncertainty. Last but not least, we don't have such infrastructure that allows the data sitting next to the computer, so we can develop learning model like immediately. So they're not seamlessly connected. And for the state of science, we recognize there are lots of development for emulators. There are also pre-training using process models, and then improve it by using the observation data. And also there are lots of good observation data set that we can take advantage of. In terms of the research opportunity, we propose to develop such frameworks that allow online and offline training could be switched on and off anytime. Like when we develop a offline model, that when you put it back, it's likely not work as well. All right, so we need to run the hybrid model for a while, and then we need to train it in an online motion using observation. So we can do this hybrid mode on and off to make sure the model is going well and generate reasonable results. And also when we develop all those hybrid models or emulators, we should not rely on just one model data set, which is in most cases, this is the case. This is the data that we have, right? Usually we use one data set from a model, and then we build the emulator. But the error or the uncertainty will be constrained or driven by that the only one model. So we propose we need MAPE-like data archive, which is like multiple model ensemble or intercomparison between different models. So we have a bunch of models which have different bias for uncertainty. So the learning can incorporate all those information together. And last, to develop all those data sets, we need more GPUs and more importantly, GPU-enabled Earth system models, which I believe it's already in progress, but we need more such capabilities so we can generate data much more efficiently. Well, we have the same ambitious goal for the long term, right? We want to have a integrated hybrid model that can speed up by 100 or 1,000 times. For the near short term goals, we propose such infrastructure which can archive different kinds of data or from different model development group, which the machine learning can develop based on those multiple data set. That would be a infrastructure needs. And we also need machine learning engineers who have good understanding of the machine learning algorithm or their constraints, or how to more efficiently tune the parameter to develop those hybrid model. And also, since our ultimate goal is develop a Earth system model and in hybrid Earth system model, so we need to have good communication between different components of the Earth system model. So people have a good understanding about which component actually is ready, which one is still not well understood. So we need to look at more information about the data set. Well, on the other hand, if we have a good understanding of certain components, then we can probably go ahead to develop surrogates for that. And last, we of course need all those communication between domain scientists and machine learning engineer and software hardware development. That's all I have. Thank you.
Thanks, Julie. Nikki, that's all from us.
Great. That's a lot. Thank you all very much. And I appreciate you putting it together in such short notice. Jim, do you want to take on the AI architecture and co-design work?
Sure. And just let me do a time check. How much time do you want us to take?
Take the time you need, everybody. We did decide today we have a lot more flexibility than we normally have. So we will open the other session. So if someone is not on here, they can log in and we'll let them know we're coming. But we're going to finish out this conversation before we switch over, and we will take a little break. So just hang in there, and Jim, take as much time as you guys need.
Excellent. All right. Well, I think first we'll hear from Sarat Sripathi and Matt Norman. We'll give a report out from our first breakout room. Sarat? There we go.
Can you see my screen?
Yes.
And first, I would like to thank Matt Norman for his help in putting together this breakout summary report. So in our breakout, we were focused on the Earth system applications, both AI, simulations, and data analytics applications at the DOE leadership computing facilities and large HPC resources. So some of the grand challenges we have identified during our discussion is how do we make use of reduced and mixed precision hardware that is available, are becoming available at all these centers for various model components. And how do we build better AI surrogates for those components, taking advantage of this hardware. A topic of discussion that came up is how do we better leverage climate co-design efforts, and what can we learn from previous history, and how do we address those open challenges. So we heard a retrospective from Phil Jones and about previous efforts, and how can we communicate to the vendors, and including the Coral 2 procurements and other vendor contracts, so that Earth system needs are heard and listened to when we're dealing LCF procurements. So the state of the science in general, super parameterization is one of those strategies that is being used where you do subgrid parameterizations and subshoot them with neural networks to get higher, for example, to get convective parameterization for cloud resolving and similar applications. There are also various frameworks which have both a usable prototyping sort of interface as well as a performant backend in C++ or other high performance languages that is more suitable for leveraging performance from hardware. There are also some AI specific hardware, as I alluded to, like the tensor cores on NVIDIA hardware, and how do we better leverage these in the Earth system model simulations. Right now, these are very low precision hardware, and we need to identify which model components can take advantage of that, and how do we integrate into the larger model. So some of the opportunities we have identified is how do we expose these resource heterogeneity that we are going to have, and how do we expose a proper API at a right abstraction level so that domain scientists can actually target those resources effectively. So some of these needs to be interplay with both compilers as well as the programming models as well. And how do we integrate languages like C++ and Fortran along with some of the AI specific frameworks. So another topic that came to mind is regarding communication, how do we better advocate for the Earth system modeling computational needs, and how can we effectively communicate that to the vendors through previous efforts included mini apps and other kernels, and how do we incorporate the AI based and hybrid modeling mini apps and applications so that they can properly inform those vendors for our design requirements. One common theme in general is we need to move into a higher arithmetic intensity regime to target this sort of hardware, and AI models in general help us to do that, and integrating them into with respect to hybrid models helps us achieve that. So in terms of research priorities, there are a few interesting cases there. When we build surrogates, there is a huge parameter space that needs to be explored. How can we exploit AI to kind of effectively search that space, and how do we cover both nonlinear aspects in a fine-grained manner and incorporate these mixed precision capabilities? And on the data analytics side of things, how do we better have the data movement challenge addressed as well as the memory wall challenge in terms of data analytics? So all these questions need to be addressed in conjunction to have a better computational utilization. So some of the short and long-term challenges we have identified are here. So APIs and programming systems, and then benchmarks for vendors, ranging from, and how do we create better AI surrogates from high resolution data? And finally, at the longer term, how do we effectively influence vendor hardware to better suit AI needs for Earth system applications? That's all from me. Thank you.
All right, thank you, Sarat. And there's one question in the chat from Siva. Hopefully you can address that. Next up, we'll hear from Maya, James, and Ivy.
Thank you. Let me find the screen to share. Let's see.
Yep.
Is that good?
Yes, very good.
Okay, well, I'm Maya Gokhale. I would like to thank James Ho from CMU and Ivy Peng, also from Lawrence Livermore, for working together as a team to put this breakout session together. This is AI architectures and co-design with specific reference to cloud computing resources. And I also, before we start out, want to acknowledge the wonderful participants we had in our breakout session. We were so privileged to have both the domain scientist side saying, here's what we need, this is what we're looking for, and also people from the commercial web services side saying, well, here's what we have, this is what we can provide. So it was wonderful to get those two perspectives and help us to organize our thoughts on what is really needed in the future. So for the grand challenges from the domain science side, we were told that domain scientists are very interested in exploring new systems. They need new hardware and new approaches to solve these very difficult problems, but they don't know how the systems and mechanisms actually work and how they can effectively utilize them. And so knowledge of how that actually occurs is important for them to be able to effectively use the resources. Another thing we learned is that while there are many, many generic machine learning models and services on the cloud, they're not exactly matched to the ESP specific domains right now. And that is a challenge to be able to address the needs of the domain scientists. So basic services on the cloud are readily usable, but there's costs associated with it. So large scale use can end up being large scale cost if we're not careful. And also there's a sustainability issue to add new domain specific services for more limited sort of application than the larger AI space. And finally, as has been noted in other sessions, protocols and tools for ESP data sharing, data federation on the cloud storage resources need to be developed. So what's going on right now? Well, cloud providers have user-friendly tools to run AI and ML workloads. The tool capabilities differ among different providers. So you might end up, if you're using Google Cloud, you're going to use very different sort of model that targets maybe the TPU than if you're using the Amazon cloud or the Microsoft cloud. Another point that came up was that cloud providers can accommodate petabytes to exabytes of data storage. And so we were told that if you want to drop 100 petabytes on our Amazon storage, that's not a problem. Exabytes, maybe we'd have to work with you a little bit, but we've seen a theme come out before that where are we going to put all this data? And cloud is a place we can put the data, but it comes at a cost for these commercial providers because the cost model is based on accessing the data. So if you want to study it, use it, do analyses over and over, that's where in the commercial cloud, the cost is coming in. We noted that cloud can provide AI at scale that really matches, in some cases might exceed DOE resources. So NLP models approaching 1 trillion parameters are a reality right now. And to repeat what we said before, the raw materials are available to create domain-specific sorts of workflows, but it's going to require some work to make that actually happen for the ESP set of uses. Because the commercial AI ML cloud infrastructure and services are motivated by text and image data, not necessarily high-dimensional scientific data. What are the opportunities? Cloud can provide virtually unlimited cycles, so collections of individual experiments, ensembles, uncertainty quantification can be accommodated very flexibly on the cloud. Cloud may facilitate data sharing due to the ease of merging distributed data sources in a central, virtually central location. Cloud includes various sorts of heterogeneous compute resources in CPUs, GPUs, and accelerators. So often we see the state of the art and beyond accelerators appearing in the cloud. However, for commercial cloud, the cost model is based on use. So that really has to be factored in for the research community. And that's in contrast to the DOE facility model where we apply for grants and have a predetermined number of hours in storage allocation that we know about ahead of time. So research priorities, again, workflows, develop workflows that incorporate cloud and work in concert with the commercial AI ML activities for that economy of scale. Develop service-oriented sort of abstractions to support the scientists by hiding some of that scale and complexity and heterogeneity. Create data formats and structures. We've seen this before in other sessions. And improve efficiency by co-design across many different sorts of technology domains. So ML and traditional simulation, computing, storage, communication, different sorts of accelerators, including together HPC, cloud, and edge. And then look into AI at scale opportunities. So for our overall vision of how this would go about happening in the short term, we need to use cloud, we need to provide tools that are in the ESP domain and really talk to the ESP workflows. In the medium term, we can enable new problem solving by combining what is available in the HPC DOE centers with cloud resources. And we could also look at improving energy efficiency of AI ML computation by better exploiting sparsity. That's a combination algorithm architecture sort of problem. And in the long term, the vision is to deploy complex integrated workflows that include simulations in HPC, so on-demand HPC clusters, heterogeneous accelerators, unlimited secure storage with authentication and provenance all together to be able to do these extremely large-scale models that we have just heard about earlier today. So that's it.
Very good. Thank you, Maya. Okay, next we'll hear from Sai Hammond, Tushar Krishna, and Maruti Marantu. So, Sai?
All right, let me try and get this presentation up. Can you see that, Jim?
Yes, very good. Thank you.
All right, great. Well, thank you, Jim, for giving me this opportunity to report out. I want to thank my co-chairs, Tushar and our reporter, Maruti from PNNL. So our session was on edge computing and kind of an Internet of Things approach. So think about this as sort of sensors integrated into Earth system measurement. So we're sensing things and we've got processing distributed around the globe, sending data back for processing. So grand challenges. This was something that we talked about a lot, right, was data movement. So if you really do distribute sensing and processing all over the globe, moving data around and bringing it back, sharing partial results from sensors to edge processing and back to some sort of cloud or HPC facility is potentially a huge challenge. It's challenging because it's expensive to provide the bandwidth, but it's just expensive in energy, very expensive in terms of power to these sites, and potentially very expensive just in terms of system cost. And this is something that's going to need a very sustained amount of focus. So energy efficient computing that is super energy efficient, because moving energy out to the edge to run this kind of processing will be exceptionally challenging. And this might be different really because in a commercial setting, and there are certainly commercial use for this kind of processing, we would have a much larger scale, potentially very vast scale in areas that are not very hospitable for sending people out to go fix things or put new batteries into sensors that require them. And then a second theme that was really sort of discussed at length was whether existing AI and ML methods really work in the context of climate and edge processing. So, the typical thing, you're running ResNet looking at images of cats online, right? And the existing ML methods do very well for that. But when you've got kind of partial data, it's scientific data, sometimes it's sensors, it's only partially available. This is kind of complicated, and it's not an area that we've necessarily seen a huge application of ML yet. Question as well is, do we do this in a federated sense where everybody's processing things at the edge and just sharing partial results? Or do we just do this locally right at the edge? Or do we do some kind of centralized processing as well and send it all back? One version of this could be that you centrally train models and you send it back out to the sensors and for edge processing. So maybe you do that on a big HPC platform and you send the model out. Another version is that you've got a distributed or federated model that's running all the time, sharing results. So this is a question that we don't have answers to yet. And then a question of funding is how do you bring data scientists and domain scientists and everything together? We typically fund these things separately, and we need a more sustained effort to have everybody come together and talk the same languages. So state of science, today ML is very good at detecting patterns, and then we can do deviations from those patterns. So I'm sort of won't talk about all these bullet points, but anomalies and extreme detection is something that we can do, but having ML and AI be sort of closer to that and maybe the events be less extreme that they're detecting is still something that's potentially challenging. One of the things we can do today is we're pretty good at doing data reduction or data selection, so identifying artifacts that are interesting, We can do some of that today, but as those things become more complicated, and the fidelity of the sensors and the information becomes more fine-grained, how confident are we that we'll be able to do that moving forward? So we can do some of this, but we still need some investment in it. We talked about several projects. I won't go into these in detail. Several of the project participants and PIs are on the call. We're very grateful for their input. But the summary of this is that there are sort of edge processing and edge sensing capabilities in ML being applied. This geomorphic computing concept from Argonne was particularly interesting. So I won't go into detail on that, but the authors and the PIs were on the call, and this was an exciting project. Okay, on to opportunities. Well, let's just say, first of all, surrogate models, we've talked about this a lot in the workshop. So we sort of definitely see an opportunity for that. So reducing the processing. But some of the other opportunities we think perhaps apply more here were, running local simulations at the edge or an HPC platform and distributing those results out and having them, make decisions around what data we're capturing, what things are important, what do we focus on? Can we use that as a control loop to basically improve the fidelity of the science that we're doing, and then infer to the sensors and everything what they should be looking for out in the field. Another opportunity is having AI and ML optimize the parameters of this huge hardware system. So you've got this enormous data collection operation around the world, all feeding data back. But, where do we run the processing? Do we run it at the edge or centrally? Where do we send the data? How do we send back control signals, and what should we be controlling and sending back? And then where do we focus the processing? So if we have this vast collection of data, can we focus it on, say, significant weather events or areas of concern? Maybe there's flooding. Can we use ML to detect all this and focus the processing on the things that are actually practically useful, for people around the world? So research priorities. This is a similar list that you've seen in other sessions. So we agree that tools are certainly an area that we need to spend a lot of time thinking about. How do we couple data from the edge into numerical simulations and integrate those into our models? It's not clear how we do this at significant scale. So just at small scale, this is hard, but with really large scale, really large data volumes and rapid data arrival, this becomes very challenging indeed. And it has ramifications for DOE facilities and for our system designs. Another one is reproducible workflows and benchmarks. So, ML, Perf, and ResNet really are not relevant, or at least less relevant, to the metrics of success that we're trying to define for these systems. And so we need to think about the true workflow of the distributed system and have a good model for that so that we can reason about the design. One thing we think about as well is, what are the benefits of running on the edge versus HPC? We don't know the answers to all of this yet. So HPC here would be a centralized resource versus, say, a federated or distributed resource. And the partition of work and how we split that up and what runs where and who is responsible for what is really not clearly understood, and certainly not in the context of data movement and energy usage. And then the last one I'll talk about here, just in interest of time, is data security. So if you're really collecting data around the world and you become reliant on those data streams coming to a central processing site, and you're reliant on some of the answers that this system can produce, you want it to be secure. You don't want it to be something that bad actors could get into and perturb. And we also just need data security in terms of consistency of data. Errors and reliability don't impact the quality of the models and the work that we're doing. And this is potentially very challenging because it has impacts on system design and performance and everything as well. All right, I'll go on quickly to just talk about our timeline. So the short term, we've got some early adopters, very early brave souls. How much pain are they willing to accept? The software frameworks and systems today are not very easy to use, and we definitely need to improve this if more users are going to be involved in this kind of work moving forward. We also need to think about how our software composes, our simulations and our ML models how do we knit all this together into a true system, not just a load of software products that sort of just happen to exchange data and values. And we believe we need a lot more collaboration between data scientists and domain scientists. Just you'll see these little last bullet points in each of these time things. So right now, inference at the edge is an area that we could improve in the short term. Medium term, maybe sort of control at the edge, right? Automatic or smart or federated control, where the system as a whole is able to steer the kind of control of the entire sensors and edge processing units. One possibility would be sort of a test facility, like a test bed environment for experimentation and design for this work, where users could come out and try putting processing at the edge and see what it looked like. That is quite difficult to do today, certainly at any scale. So that would be a medium-term goal. And then long-term would be sort of true federated learning over streaming data, where it's continuously coming in across all our sensors. We're doing learning everywhere, and we're sharing the partial results and updating our models as we go. And that this is a continuous operation, not something we have to do ahead of time and send out, or that we have to keep periodically updating. We want this to be a very smooth process. And then, longer term would be something like a digital twin. You have almost like a digital twin of the globe, that all of your sensing data is going into a large model, and that you're able to replicate results and then use it for predictions moving forward. And this would be something we would see as running continuously. So that's it from us, Jim. Back to you.
All right. Thank you, Sai. Let's see. I think I just want to reiterate one point that Sai mentioned. And I know we're not supposed to talk about their need for funding, but I did want to talk about how under co-design, we might want to rethink or at least think about how funding for things like FOAs is structured. Funding opportunity announcements, of course, are always targeting a specific domain. It could be a specific earth science topic of interest, or a computer science topic of interest, or an AI ML topic. But how co-design is funded is actually a very, maybe a larger question, and maybe it requires establishment of something like a research center. They're the NQIS research centers as a particular model, but it's just something for our DOE leads to consider, that co-design is not an easy thing to fund, because by its very nature, it needs to be multidisciplinary. So with that, I will pass the mic back to you, Nikki.
Thank you, Jim. I do think that we've heard repeatedly throughout the workshop that there needs to be a culture change across to bring these groups together that would be involved in the co-design, and that would be involved in crossing the computational mathematical side with the domain science side. And so I think that theme goes beyond even just what you were saying there, but how do we do this culture change so that we have active things to work on, and it's not just left to everybody's spare time? As we all know, we don't have a lot. So I want to thank you all very much. I appreciate it. We are going to take a 5-minute break here, and we'll get over to our sessions as soon as we can, but I'll give you at least 5 minutes before we spin those up. So thank you again for the last public session, and those of you who are going over, I'll see you in a moment.
And just to be clear, Nikki, we're using the normal private session link, not the seminar link, correct?
Yes, the same link for all the invited sessions will work this afternoon.
Exactly.